LeetCode Daily Challenge, Problem 863, O knows distance k in binary tree. The problem description is that given the root of a binary tree, the value of a target node, and an integer k, we would like to output or return an array of the values of O nodes that have a distance k from the target node. The example raised in the problem description is this binary tree. Given the root of the binary tree, which is 3, and the value of a target node, which is 5, and then an integer k equals to 2, we want to find all the nodes that is distant 2 away from the target node 5. So how can we acquire the distance from the target node to each node? So by definition, is the number of edges between two nodes. It's the distance between the two nodes. So nodes that have a distant 1 from the target node is 3, 2, and 6. And nodes that have a distant 2 from the target node are 1, 7, 4, and vice versa. Nodes that have a distant 3 from the target nodes are 0 and 8. Distant 1, distant 2, distant 3. Okay, distant 1, distant 2, distant 3. Okay, so in this case, the desired answer is k distant equals to 2, which is distance 1, distance 2, distance 1, distance 2, distance 1, distance 2. So we should output 7, 4, and 1. So this is one of the approaches. Step 1, we would like to transform the binary tree into a undirected graph. Step 2, after the construction of the undirected graph, we will traverse the graph via breadth first search, and we will start the breadth first search starting at the target node. Starting from the target node. And in each iteration, we will explore all the nodes having distance I from the target nodes. And after k iteration, we will finally explore all nodes having k distance away from the target node. So step by step, we will introduce how to implement step 1 to transform the binary tree into an undirected graph. We still use the example in the problem description. First, there are various ways to represent a graph. So it really depends how are you going to how are you going to represent your graph. In this in this case, we 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 are going to represent the graph by an adjacent adjacent adjacency list. So this is a simple code to transform a binary tree into a undirected graph. First, we will input a null pointer and the root node of the binary tree. Since following the code, it basically const uh, it basically build construct the adjacency list by inserting the parent into the adjacency list of the child node and insert the child node into the adjacency list of the parent. So to initialize, we input the null pointer and the root. And since the the inputted node is null pointer, it will it will it will go through line 22 and 23, and this is a recursive to explore to transform all the nodes on the left child of the root node. And similarly, in line 24 and 25, it will transform all the nodes in the right subtree of the root node. And this is a simple walkthrough of how it is implemented. So first, we traverse the left subtree. It will recursively look for all. It will recursively add the nodes that are connected, that is in a binary tree, that are in a relationship in a relationship as parent and child. So, for example, in this case, if we input the root and the root left, then we will build according to line 19 and line 20. We will augment each adjacency list of the parent and the child node by another. For example, for the adjacency node of the root, we will append the left left the left child. For the adjacency list of the left child, we will append the root. Similarly, we can recursively call the function in this manner. We will finally build all the adjacency list of each node, and we can get the representation of the undirected graph. This is the first step. Transform the binary tree into an undirected graph. The second step is to undergo a BFS, a breadth first search. So starting the BFS will start at the target node, and in each iteration, it will explore all the nodes on the ith have having a distance I away from the target node. So that's implemented. First, first, so step one, our approach is step one, transform a binary tree. Okay. Transform the binary tree into an undirected graph. Step 2 is to traverse the graph via BFS. Okay. Tree to graph. Null pointer and the root node. So after this, so this basically is to get the adjacency list representation of the transformed undirected graph. Okay. So the adjacencies we will declare a variable to store to store the adjacency list. Okay. Its type should be like, given a node, we will find all the neighboring nodes of the given node. So we can use what should we use? CPP on order set. Okay, then we make use an unordered map. Given a key, we'll find the given key. A key is the given node. The return value will be the adjacent all the neighboring nodes. Okay, std value type key pair. Okay. DQ. On order map. Okay, on order map is a key value pair. Okay. Okay, key. So the key is a node. Is a node, tree node, pointing to the tree node. Okay, and the value should be a list, or in C++ as a vector of nodes. Okay, and alright, let's see. And we also need to define the function here to transform into a undirected graph. Okay, so given parent node, child node. Okay, if parent node not equals to null pointer, then construct insert let's see, add adjacency list parent node pushback because it's a vector. All right. Pushback child node and vice versa. For the child node, we will insert the parent node into its adjacency list. After this, we will recursively call the tree function for the left subtree and the right subtree, of course. Okay, child then we'll recursively call itself, but this time the parent node will become a child node, and the child node will become the left subtree. Left, right. Similarly, for the right subtree, okay, then it's done. It should be fine. So step 1 is completed. After calling this, we will get an adjacency list representation of the transform undirected graph. Okay, step 2 is to traverse the graph via BFS. Okay, so BFS is quite standard. We need a queue. Okay, each queue will store, of course, a tree node. And we need to remember all the visited nodes. Okay. In order to find out whether a node is visited or not quickly, efficiently, we can use the unordered map, because the find function is basically the complexity of the find function is, where's find? The complexity of find function is constant, basically constant on average, but the worst case can be linear. Okay. Okay, so we will use unordered map where each element is also a tree node pointer. So at first, we'll of course BFS starting from the target node, right? So what I'm going to do is to push the start target node into the queue, and also mark the target node as visited. Now this one, insert. Okay. Okay, then we will start the iteration for distance. So distance means the distance from the target node, starting from 0 all the way to k minus 1. Okay. So in each iteration, in the kth iteration, we will explore all nodes having a distance k away from the target node. Okay, it's quite simple. It's quite simple. So in each iteration, we will explore all nodes having a distance k away from the target node. So we will first, okay, pop, find the find a node, call it current node as the front of the queue. Okay, and don't forget to pop it out, and for each neighbor in the adjacency list, okay, here, adjacency list of the current node, if the neighboring node is not have been visited. So if neighbor, we would like to know whether it has been visited. Find neighbor not equals to. So how to use the find function? It's an unordered set, right? Unordered set. Okay. Unordered set, right? Okay, the find function. Okay, the return value return path, iteration. Mm-hmm. Let's see. Find. Hmm? On order set, insert. No, not insert. Is find. Find. This one. Okay. Find the element with key that compares equivalence to the value x. The overload part is of any overload resolution only. Blah 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 blah. Return value. Iteration to an element with key equivalent to key. If no such element is found past the end, iterator is returned. Okay. So the end iterator. So this meaning that if it does not equal to the end iterator, meaning that we can find it in the visited node. So since we have visited it, we will skip on to the next neighbor. Otherwise, if the neighboring node has not been visited, then what are we going to do? Then we are going to, of course, add it into the queue, right? Okay, replace, and of course, mark it as visited. And that's it. So after the k iteration, O, after the k iterations, all the nodes in the queue will have a distance k away from the target node. So we can find out our answer. So the public return function is type is vector of integer answer. While queue is not empty, then we will do the following. Answer the pushback queue dot front dot how this go value, right? Okay, and don't forget don't forget to pop it out, and we can then return the answer. Let's run that. Compile error. Line 51. If no matching member function for code to find. Okay, no find. Visitor node is an unordered set. No such function, unordered set. Okay, find. 変だな。違うか。ここ。Okay. Find. Okay, here. Again. Let's see. Line. What the fuck? 100. Cannot be no pointer points here. Okay, which requires 8 blah 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 blah. Select some memory stuff. And let's see. Unordered tree map. Adjacent list. If depth not equals null pointer. Okay, parent not equals to null pointer. And push it. Null pointer root. Okay. Push insert. Okay, this is not K++, right? And of course, what the fuck is K? K, this is, okay, K, should be fine. Line 62, K dot front value, Q, member access within misaligned. Well, so let's answer the pushback. Okay, push, is that the correct? Alright, memory, undefined behavior and sanitize undefined behavior, proc join. For type tree nodes. For type, why it is tree node? Q dot front. We insert a neighbor. Is that this one? Run. None not equals to Q dot front. Okay, value. Stock. I'm stocked. Tree node. Doesn't matter, right? What the fuck is it? Insert. Push. Starting. Okay. Initialize. Okay. Insert visited. Distance starting from 0. Smaller than K. Tree node. Current node, right? That's fine. Equals to Q dot front. And pop it out for each neighbor of the current node. Okay. What did I miss? What the fuck? Void. Parent. Child. Okay. Sanitizer. Where's he? Okay. Q dot front For each if no such element is found, it not equals, then okay, visited. Q unordered set. Unordered set. Okay. Unordered set. Q unordered set. Vectored int q dot front. If not empty, and 62. Let's say insert a random value in it. What's wrong? What's wrong? Empty. Okay, distant. Well, this iteration stop. Yes, it will, right? Let's see. Distance k. Root. Target. Okay. Okay. Left, right. Okay. To the root and the traverse Q. Tree node to visited. Push. Insert. Okay, insert. Find. Insert. Okay, 0, 2. 0. Okay, 0. What's 0? No, 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 no. How should I say? Okay. For each iteration, we have a queue. Okay, current. Oh right, oh right, all right, all right. For each, what the fuck am I doing? So for each iteration, we first need to know how many nodes are there currently in the queue, right? So this n is basically the number of nodes having a distance dist, right? Away from the target node. All right. Then then we will no this one. Uh, then for for each of the nodes, of course, the following the description is the same, right? For each of these nodes, um, we are going to right pop it out, right? Of course, to pop it out, and if to find the four, okay, pop it out, um, pop it out, and we are going to examine. We are going to examine its neighbor neighboring nodes. All right, right. Pop it out. Examine its neighbor. If it is not visited, then adds into the queue and then mark it as visited. Right. All right. That should be fine. Let's see. That should be fine. Queue the front. The value. Right. Let's run it. Okay, accepted. Submit. Right.